Hello, everybody. So today I will talk about this question. Merge binary search trees to create single binary search tree. So this question is extremely hard. So it took around 5 hours to come up with the solution for me. It took all of n log n time, and actually it was time limit exceeded. So I, but after that, after an hour, I could solve the question with O of n time complexity, and it was accepted. Yeah, so today in this video, I will introduce that O of n time complexity approach. So let me get started. Okay, so in this question, I'm giving n binary search tree root nodes in an array. And each binary search tree has at most 3 nodes, and no 2 root have the same value. In one operation, I can do something here. So basically, let's see, in this case, I have 2 trees, trees 0 and trees 1. And now, the leaf of trees 1, this one, node 2, has the same value with the root of the tree 0. So what I can do is I throw away this leaf node 2 and put this root node 2 from tree 0 to here. And then it looks like this. So this node 2 comes from the root of the tree 0, not the leaf node. Yeah. So this is something I can do here. And in this question, this is a root and this is a leaf, obviously. And in the case when a tree consists of only a single node, this node is considered to be a leaf and also a root. So this is something I have to take care. Okay. And my task is to return the root of the resulting binary search tree. Yeah. Or null if it is impossible to create a valid binary search tree. And this is the definition of the binary search tree. Okay, so this is it. So I will introduce the approach I took. Okay, so in this question, as I said, I'm given the list of 3 nodes, and I will return the 3 node object, which is the root of the merged binary search tree. So in this question, I'm given the list of 3 nodes, and I return the 3 node, which is the root node, or null, if I cannot merge into a single resulting tree. So for example, let's think of this case. Example 1. So in this case, what I noticed first is that this 2 is equal to this 2. Yeah, the root of this tree is equal to the leaf of this tree. So I can merge it. So I merged it. So what I have to take care is that when I merge this and this, I throw away this leaf node and put this root to here. And this is it. Okay. And next, I have 5 and 5 here and here. This is a leaf node. This is a root node, so I can merge them. So what I can do is I throw away this leaf node and put this root node to here. And 4 comes here. Okay, this is it. I just demonstrated what I should do in the example 1. So far it's very simple. So that being said, let's think what I can do from here. So what I notice, the learning from here is that I should merge the, 2 trees if the leaf of one tree is equal to the root of another, the other tree. So far I'm saying nothing special. Yeah. And also, what I want you to notice is that I'm given the binary search tree, list of the binary search tree. So the tree itself is binary search tree originally. So what I can say is, I hope I find the merged merged tree from this leaf node. So if I can find the root node, which is equal to this, I can merge that root node to here. So from here, what I should notice, I actually noticed immediately, but finally I noticed is that I can decide the root node. So root node in the resulting tree shouldn't be merged with any leaf. So this means that let's take the hash map of the leaf nodes. And I check, so in this case, 1, 2, 5, 4 should be the leaf nodes. Yeah. And for each tree, I see if this root node 2 is in the hash map. And if it is true, I can merge that tree, to that tree. So I'm checking root node 2 and I have the hash map for this 1, 2, 5, 4, and I can find 2 in the hash map, which means that this should be merged into this. Okay. Next, I take a look at node 3, and 3 doesn't exist in the hash set. So I can say this 3 should be the root of the resulting tree because it cannot be merged with anything else. And for this 5, I can say I can find the node 5, value 5 in the hash set of leaves. So I can merge this 5 to here. So at least I can say with this approach, I can find the root node. But there is a case that I cannot find, I can find 2 root nodes whose value doesn't exist in the hash set, or maybe more. Yeah, this is very simple like this. So let's think of this tree and this. So when I do this, the hash set of the leaves should have the values 1 and 2. And when I take a look at node 3, root 3, 3 doesn't exist. So this should be the root of the resulting tree. But for this 4, it doesn't exist in any leaves. So this means that this should be the root. Yeah, so there are 2 root nodes. So this means that the merging is impossible in this case. Please try to find the merging way. It's not possible. So that's what I want to say. Okay, so let's write the observation, what I found from this example. So first thing I can do is find the resulting root. So for this, create the hash set of leaf values. Check, or I should say if the root var doesn't exist, I should say, isn't included in the hash set, it's the leaf node. So sorry, it's the root of the resulting tree. Yep. And I do this. And in the end, as I said, if there are 2 or more such nodes, I will return, none. Because as I said here, it's not impossible to merge all of the trees into a single binary search tree. Okay, so what if there is no such a node? Each root node value has, for each root node, there's somewhere a reef node which has the same value. And let's think of that in this way. So in that case, let's say I could finally merge them into a single tree. Looks like this. I don't know. But what I can say here is still this root node exists. I mean, this root node value 1 exists as a reef somewhere. So this is obviously invalid because this and this has the same value, but in the binary search tree, no two nodes can have the same value. I can say it's invalid, even if I can create such a tree. And as a side note, I can see here that, where is it? No two roots have the same value. So this means that this one is not paired with any other root node aside from this. So even after creating the, binary search tree, which is merged into a single one, this one still hasn't found the pair aside from this, and obviously this and this has the same value. So this binary search tree is invalid. I can say 0, 0, or 2 or more such nodes, I return none. So in the end, in this way, I can find the resulting root. Okay, so just keep in mind that, the given array can have the tree which consists of a single node, which looks like this. So let's say I have 1, 2, 3, and I have the node, 4, which consists of the tree by itself. In this case, 1 is not found in 2, 3, 4 is not found in 2, 3. So 1 and 4, both of them are the candidate of the root node in the resulting tree. So this applies to this case, I return none. This makes sense. And let's say I have like something like this. So in this case, this 3 inside of the reads 2, 3. So this is not the candidate of the root of the resulting binary search tree. So actually this is the root of the resulting binary search tree. The candidate of that is only this node. So yes, I can conclude that this is the root of the binary resulting tree, and I can merge this to this. So what I want to say is, I just showed you the example of trees which had only 2 or 3 nodes, but even if the array includes the tree which consists of only a single tree node, this way, this approach works. I just wanted to know, clarify that. Okay, so that being said, now I could find the root node of the resulting tree. So even though I could find the root node, this doesn't mean I can, merge all the trees into a valid binary search tree. Even after this, the operation can fail. So what I mean to say is, let's say it looks like this. So in this case, yes, I can merge this 3, 0 to here. So 0 should come here. But what I'd like to create is the binary search tree, and the 0 is smaller than 1 or 2. This is invalid. So what I want to say is, after this operation, I try to create the binary search tree with this root node, but it still fails. And I have to do the validation for that. I keep track of the relationship of the values in the nodes. Okay, so once I find the root node, how can I merge trees into single node, single tree. So let's say I have this case. So here I can use the recursion. So I start from this root node. This is the root node I found here. And then I take a look at this node too. And I try to find the tree whose root is 2. And I can find it from the hash map. And then I connect it. It looks like 3, 2, 1. And after that, I try to find the root node whose value is 1, which should be merged here. I will try to find the root node. Yeah. I think I can use the hash map of like root node to tree mapping. But in this case, I can't find any tree which should be replaced. Sorry, which should replace this root node 1. So that's it. I don't have to continue it anymore. And let's say this root node 2 has some child node. Then I have to find the tree which should replace that reef node. So I try to find it. And if there is, I should replace this tree node with such a tree. And if I replace, with the tree, and I have the child nodes, if I have the child nodes, I also have to find the tree which should replace such reef nodes. I have to continue that recursively. So, as I said, I have to do this recursively. The recursion is the best choice here. So recursively, start from the root node and recursively build tree. I think this is enough. Okay, so this is something I can do. Yep. And as I said, it is possible that, as I said, if it is possible that the constructions of the tree fails because of the relationship of the trees. So take care of the values relationships. Okay, so this is something I can do. And in the end, if I could create, return it. So what I mean by returning the resulting tree is returning this root node. Okay, so this is it. So this is the basic idea. So let me get started with the implementation. Yep, I will talk about the details of this or something others in the implementation part. Okay, so as I said here, what I should do first is find the root node. So let's create the helper method, find the root. And it is possible that I find 0, 2 plus nodes, root candidate. In such case, let return none. So this means that if this root is none, I should return none in the main method. Okay. So this is about the first section. And then the second section, I have to build the tree recursively. So let's define the function, recursive function, build tree. And for this, I pass the root Yeah. And I try to construct the tree. And obviously I have to know the, I mean, other nodes in the trees. So one possible idea is pass the trees to here. But I think another idea is that I create the hash map like this, remaining tree. And as I said, every time I build the tree, I have to find the node which has whose root node has the same value as the current node. So let's say I have 3 to 5 and I try to create, I try to build the tree from this node 2. In that case, I have to find the tree whose root value is 2. So I should put it in the hash map so that I can find it quickly. So I can do it in this way. Okay, so I created the hash map. So I pass this remaining nodes to this hash map. But obviously, because I start from the root, I have to delete root from remaining nodes. So I can do it in this way. Yep. So in this way, root 3 is removed. Not included in this hash map. Okay. So I call this build tree with root and remaining nodes. Okay. So as I said, this build tree can fail. So in that case, return none here. So if I couldn't merge, I should return none. This is it. And also, one more thing I have to take care is, even though I could create a tree, binary search tree, it is possible that there is a node. There is some nodes. Sorry, this should be remaining trees. So, even if I can create the binary search tree with this recursion, it is possible that there are some remaining trees. So if there are some remaining trees, I should return none because I couldn't merge all of them into a single binary search tree. So my idea is remove merged used tree. Used trees are removed later. So in this way, if I find a tree and if I merge it to the merged tree in construction, I remove that tree merged from this hash map. In this way, I can say if there are remaining trees, I should return none. Then in the end, I could create the binary search tree, so I return the root. Yep. So this is the basic idea of the main function I will implement. So now my task is to implement the helper methods. Okay, so let's get started with the first helper method, find root. So what I will do is this one. I just copy paste it. So creates a hash set of reef nodes, reef values, and then I do the iteration, and for each tree, I see. Check if it is included in the hash set. I see. So I can say, Firstly, I create the ref bars. So what can I do? So, oh, I have to make it hash set. So for tree in trees, if this is it, and do the same for the right child in this way. Okay, so now I've got the ref bars hash set. Then here, I do the next iteration, second iteration. So root candidate. Yep, so I do it in this way, and finally I get the root candidate. And as I said, I have to validate this. So if this is not 1, I should return none. Otherwise, I return root candidate. That single one. Yep, let me quickly clean it up. Correct this. Okay, so this is implementation of the helper function find root. Oh, I forget something. So it is possible that this tree is a single node. In that case, I can say this tree.var is the ref node. I have to take care of that. Sorry. So that being said, I think the good approach is create the function here like this. So in this way, I don't have to take care of this. Here, so in this way, I can say I can find the ref bar. So I append it to the ref bar set. Yep. And here I implement this. So in this case, this tree consists of a single node. So I return tree.var. Yep. Otherwise, I do this. Okay. Yep. So this is it. So I've fixed the find root method. Yeah. It looks good now. Okay, so now I implement the build tree method. So let me move it up so that I can see it with the main method. Okay, so here the idea is that I try to replace. So I try to replace this root node with another tree in the remaining trees hash map. And what I just noticed is that if I try to replace this root node, I have to know the parent node because what I have to do is something like parent.left is new tree or parent.right is new tree. Or maybe yeah. So I think passing root is not a good idea. So yeah, so let me think. Okay, so let's do it in this way. So I pass the parent node and also the root node. So in this way, I can do something like parent.left is root or parent. No, it doesn't work. Okay, so I've come up with something. So actually, I don't have to put the parent here. My concern is that, let's say I'm given something like the root, which is looks like this, 1, 2, 3. In this case, I'm given this, and my task is to replace this with this. So I can do it because I have the parent node. I can do something like root of the left is something new tree, or root of right is new tree. But the problem is the case, this root, actually tree, is a single tree, consists of single node. In this case, I have to find some other tree which replaces this node 1 and replace this one with 1, 2, 3. In that case, I need the parent because what I have to do is parent.left is something or parent.right is something. But this doesn't occur because of this constraint. No two root have the same value. So this doesn't happen. So that's why I can say I don't have to pass a parent here. Okay. Let me explain this again later. So here, I built the tree. So that being said, let me rename this a tree. So actually this is root tree. Let me rename it. So root. Okay. So now what I can do is return none in the invalid case and I build the tree. So yeah. So if this root tree is a I mean I can return root tree because I don't have any other tree which should be merged with this tree because of the reason I said. Yeah. And here I have the root dot left, the root dot right. Those should be replaced with another tree if possible. I will show you an example. Simply, I can say if I'm given 1, 2, 3. So firstly, I try to replace this 2. So in this case, this is a var, and I try to find it from here. Let me make it instance variable. No. Sorry, I have this one here. So this is the right tree. We should replace this node. So I can say root dot right is right tree. Yep. Then I do the same for root dot right. Sorry. I should start with left. Yep. And I should do the same for root dot right. In this way, I could replace this. Then what I should do is here, after replacing the tree, let's say it looks something like, oh, wait, change a bit. Let's say I've got, sorry, this isn't binary search tree. It doesn't matter for this explanation, but quickly update it. Let's say it looks like this. So I replace this 10, node 10 with this tree. In that case, I have to, merge other trees to this node 10, or I should say this tree, 10, 5, 15. So I should call build tree with this. This guy, this tree. Okay, so I kept doing it. Same for root.right. Yep, and I kept doing it. Good. One thing I want you to notice is that, oh no, wait. As I said, I have to delete this root, this tree from room trees. I mean, if I use 5, 10, 15, I'd try to remove that tree from room trees. So let me do that here. Good. Okay, now I want you to notice something. So I deleted this room trees. Sorry, I deleted this tree from the room trees hash map. And actually this room trees is now mutated. And if I look back, this room trees is shared across all the recursive functions. But in this case, in this algorithm, it's fine because the same tree is not used more than twice. Yeah, and let's say I use the tree something here, and here, what should I say? I use 10, 5, 15 here, and this is removed from the hash map. The good thing is that here in 30, it never would like to use the removed tree because of the relationships of the values. This one is definitely larger than this. So it never would like to use, or I should say, this one never looks for 10 something, a tree whose root is 10. So in this case, it's totally fine to remove the used tree from the rem tree's hash map. Okay, so this is it. And here when building tree, I return the result merge. So I return tree because I could merge. Yep. But there is one more thing I have to take care. As I said, it is possible that even if I can find the replacing tree, it's possible that it's invalid to build the tree. So it's a case look like this. So let's say this is 100. This violates the binary search trees, property here. So I also have to take care of that. So how can I take care of that? So when building the tree, I do the validation that replacing tree is inside of the valid range. So what is the valid range? In this case, the valid range here is for this one less than 10. For this one from, more than 10 but less than 20. So I need the lower bound and upper bound of the merged tree and validate that merged tree meets that requirement. And what if in this case, oh, it doesn't meet the requirement, I should use it later? No, I cannot use it later because it has 10 here. And let's say somehow I merge this 515 here what happens? Now, this means that there are 2/10, which violate the binary search tree's definition. So I can say, if I find the, you know, replacing tree of this node, and if that replacing tree doesn't meet the requirement of the lower bound and upper bound of values, then I can immediately say merging is impossible. I should return false. Yeah, so that's what I will implement from now. So as I said, I need the lower bound and upper bound of the tree. So firstly, I can say I can choose any tree. Sorry, here. So I start from minus infinity to infinity. Yeah. Then here, when I find the left tree, I do the validation. So let's create the helper method here. So for minivar, because the given tree is always the binary search tree, I can say this. And I return this. So I use it now. So with this, I do the validation. So I can say, so left tree minibar, left tree max bar. So I have to meet that left tree minibar is larger than the row. Or max bar, sorry, and no, left tree max bar is smaller than high. Otherwise, I return false. Okay. And here, when I call the recursive function here, I have to update the low and high from this. So because I merge something here, let's say I merge this and this. So in this case, originally the range of this was minimum mass infinity, upper bound 20. And here I merge this tree, and let's say this. I'm looking as a left child, so I'm taking a look at this. So low hasn't changed from mass infinity, but upper bound is now root dot var. So I said low doesn't change, but upper bound is now 3 dot var. Yep, so this is it. Okay. So next, I do the same for root dot right. Here, after getting the right tree, I find the minion max. And then I do the validation. So in this case, I add something on the right child of the given root tree. So I replace this 30 node with 3, which looks like this. Here, so the condition it has to meet is I take the minivar and maxvar, and if it doesn't meet this requirement, I should return false. Then, when I call the recursive function, I take care that, so min, this is the invalid case, this is a valid case. Min should be updated with root.var, but max, currently infinity, doesn't change. So I do it in this way. Okay, so I've done with the build tree implementation. So let me run my code. Okay, I submit. And syntax error. This one. Oh, by the way, I noticed something here. So in this case, I should return true because building tree, it should return Boolean. Oh, and actually, I said something quite. I said something wrong. So I said return false, but I returns Boolean. So returns true if success. Sorry, returns false invalid if invalid. And sorry, build tree, this method. Actually, this method, two things. So number one, return false if invalid. And also mutate the given root tree. Okay. That being said, you see, so this should be leaf bars. Good. For this case and this case, it looks good. But for this case, I couldn't return. I returned none. Why is it? So let me take a look step by step. So firstly, I'd like to see what's the root tree candidate. Oh, I couldn't find anything. I think that's the problem here. Because this should be the candidate. Let me see. Here in the find root method, one, two, four, five is the root. Leaf node values, yes. And I take a look at each tree, and tree.var is not in leaf vars. It should be root candidate. Yep. Looks good to me. So now I have this node 3. Yeah, node 3 only. Looks good to me. So I return the root candidate index 0. Wait, this looks good. But here, root 3 it didn't print anything. So none is returned from this find root method. Let me print this out. this is 1. So this is true. So I returned root candidate 0. But wait, it printed out as none? What's the problem with this? So returned. Wait, this is returned. But here it became none. I see. So I need to return. Sorry. Terribly dumb mistake. Okay. Yep. So now I went through the, this part. And now I have an error in the build tree method. Where is it? Here. So root, no, it should be root tree. So this should be root tree.bar. Okay. Missing one requirement argument. Oh, I have to pass rim trees. And here too. Okay. So here, I see. So even if root tree.ref exists, so let's think of this case. Yep, 10 exists in the, root tree is this 10, 20, 30, and I'm looking for the replacing tree for node 10 here because root tree.ref is not known. But obviously, if it doesn't exist, I don't have to do it. So I can say and root.tree.ref.bar exists in rim trees. In that case, I do the I recursively build the tree. What should I say? I recursively replace the I replace this node 10 with another remaining tree. And I need this in here. Okay. Oh, now I passed this case, but now I failed at this case. Where is it? So let's check what happens after recursively building the tree. Here, could merge is true, but remaining tree is not. So when I take a look at this example, oh, actually I can merge, but this, violate this, this 6 violates the relationship of the values in the binary search tree. So the, upper bound and lower bound, something is wrong. So let's take a look. So in this case, when tree 5 is called in the recursive function, when the tree 5 is the argument of the recursive function, low and high is minus infinity and infinity. This looks good. When 3, minimum should be mass infinity, and upper bound is 5. Yeah, looks good. Obviously, this should violate the upper bound. Let me check. So here I took a log as the left 3, minival and maxval. Let me print it out. This should be 2 and 6. Yes, 2 and 6. This is correct. And now, left 3 maxval. This is 6. Should be less than high, which is 5. Wait, so low and high is not updated when 3 is called with 2, 6. Where is it? Because I saw when, wait, I'm calculating this before I call the build tree with ref child, as I can see from this order. Left 3 minibar, left 3 maxval, 2, 6. I'm a bit confused. When 5 it minus infinity and infinity. Okay, maybe I find the reason. So when this recursive function is called with this tree, 5, 3, 8, low and high should be minus infinity and infinity. Yes. And when this recursive function is called with this tree, 2, 3, 6, upper bound should be 5, lower bound should be mass infinity. But here, I take a look at the ref3 mini bar and ref3 max bar before calling it. So this is why it is wrong. So I should do the validation of the values of the given tree at the beginning of the main method. I mean, recursive function. So here, I do the validation. And actually, I don't have to take care of the left 3 minival or left 3 max val here because it should be checked in the child recursive function, child function. I don't need this, but instead, when I call this, yeah, I have to, remit, narrow down the scope. Okay, so I don't need it here, but I do the, scope limitation before calling it. And here, as I said, I do the validation here. So I do code this and minibar max bar. So do the validation this way. Okay, let's submit it again. Oh, it broke. So here, here it doesn't work. Let me check. Okay, I see. So I shouldn't have deleted this. Try it again. Okay. So case 2. So let me check again. Oh, here. So for node 5, I call the recursive function with minus infinity infinity. Yes. For node 3, I call the recursive function with 5. Looks good. So here, let's take a look at minibar max bar. So here, when 3, this recursive function is called with node 3, minibar max bar is 2, 6. So 6 is less than 5. This is not true, so I return false. Okay, I see. So with this false should be, propagated up to the main function. Here, I need to check could merge here, and if could merge is false, I should return false. Yep. And I have to do this for this. Okay, so let me try again. Okay, now I passed. There is a print statement before I submit. Okay, so now we'll submit my code. Okay. Wrong answer. Yes. So this is the edge case. Yeah, I actually noticed this. I mean, I actually couldn't find this case when I first served this question, but I intentionally left this test case not fixed until now, so that I don't, make the explanation complicated. But here, when the B has only, the given array has only a single tree, which consists of only a single node. This is the edge case. So in this case, what happens is that, firstly, I cannot find the, here in find root method, I cannot find any root node because 7 is root and also 7 is reef. So this root value 7 is inside of the reef values, which is only 7. But I have to handle this as a different case. So here, if there is only single tree and it's single node tree, I can say this itself is a binary search tree. I return it. Okay. So in this way, I can handle this edge case. Sorry, this should be 1. So I submit again. Okay, good. Now it's accepted. So for time complexity, this takes overwhelming time because, so firstly, I try to find the root node. What I did is, firstly, Where is it? Here I did the linear scan of trees to create the file set, and then I did the linear scan again to find the root candidate. So I did the linear scan twice. Yeah. Searching in this hash set takes only the constant time. I mean here. So I don't have to take care of that. So in total, it took all of n time for this find root method. And for the build tree recursion, it takes exactly all of n time because each tree is visited only once. So assuming that there are n trees in the given array, it takes O of n time complexity for this recursion. So in total, it takes O of n time complexity. For space, yep. Here in find root, I created the hash map, the hash set, which takes O of n space. And here in rim trees, O of n space. And for the recursion stack can be up to O of n. So this is the case like the build tree, merge resulting tree looks like the linked list. So for example, every time I merge the tree into the right child of the tree. So in that case, the recursion can be, recursion stack takes O of n space complexity. And aside from that, inside of this function, I didn't use any space, which is non-constant. Yep, so in total, it takes O of n space complexity. Okay, so this is it. Okay, so I will quickly wrap up. So today I saw the question, merge BSTs to create a single BST. So in this question, I was given the array of binary search trees, and my task is to, merge those binary search trees into a single one. And if it's not possible, I return false. Yep. So in my approach, the first thing I did is to find the root tree, and then I recursively built the binary search tree. I merged the trees into the resulting tree recursively. Yep. And what I had to take care is that, when building the tree, I have to take care that the relationship of the values in the tree is good. So binary search tree has the constraint on the values like this. So I make sure that this is met. And if it doesn't work, I should return false from this build tree method. Okay. And also I had to take care if there is a remaining tree in this hash map, I should return false. None. Yeah. And also I had to take care of the edge case in which tree consists of the array contains only a single tree, and that single tree consists of only a single node. So this is the edge case I had to take care. Okay, that being said, I finished my today's coding explanation. Thank you so much. Bye.